Hello mathematicians, we're now going to have a look at the hyperbola, and as we've mentioned in class, much of the work on the hyperbola will mimic that we did on the ellipse. So it gives us a little bit of a structure for being able to organise our thoughts. So the first part is that a hyperbola is defined as the locus of all points for which the ratio of the distance from a point to a focus compared to the distance of the point to the directrix is greater than 1. So by our definition of eccentricity, that means eccentricity is greater than 1. The general equation for a hyperbola is this, so you'll notice that it's different to the ellipse because it's got a negative sign here, and eccentricity is this, and again the difference is a different sign. It was a negative in the case of the ellipse, a positive in the case of the hyperbola. I guess I am working on the assumption that we know what a hyperbola looks like, and perhaps that's a big assumption because when we've done hyperbole in 2-unit, we tended to do what's known as rectangular hyperbola. So they're in these quadrants here. We'll get to those later on, but strictly speaking, the hyperbola is of this form. So, or also of this form. So this is the one that we'll be working on initially, the hyperbola in this sense. And again, it's a conic in that it's a slice through a pair of cones. You might need to refer all the way back to, I think, the first video. Let's have a look at this diagram before we jump to GeoGebra. We'll notice that we've got a point sitting here. We've got the distance from the point to the focus and the distance from the point to the directrix. You'll notice that the directrices are A on E, and they're a smaller value than where the vertex is, simply because E is going to be greater than 1. So when we divide by something greater than 1, we get a smaller value. Likewise, the focus, because it's AE, is going to be beyond the vertex. So it's inside the hyperbola, if you like. And the ratio of PS to PM, which is the eccentricity, is going to be a value greater than 1. In this case here, it's 2.39. We might mention a couple of other points here. As always, we could find the equation of the vertex by setting y equals 0 into our equation for the hyperbola. We also have these lines here, which are the asymptotes to within which, if you like, the hyperbola is trapped. So they're the asymptotes, and they're plus and minus bx on a. So let's jump now and actually have a look at GeoGebra. So here we have our hyperbola. Remember, it's x squared on a squared minus y squared on b squared equals 1. So I've got the value of a set to 3.9. The value of b will be determined by the eccentricity that I've set for this particular parabola. So as I vary the value of a, what happens? Okay, you can see that it just changes the curvature, if you like, of the hyperbola. And if I vary the eccentricity, so I bring that back down closer towards 1, you'll notice that effect. So the asymptotes assume greater angles, so the branches of the hyperbola are much more curved as I change the value of E. But what we notice is that once the value of E is set, so E is 2.2, that's also the ratio PS to PM, point to focus, point to directrix. That doesn't change as I change the value of A. It's fixed by the ratio of A to B, and B is fixed by having E set on this diagram. Now this part we've mentioned previously, but again the foci are of the same form as for the ellipse. The directrices are the same. Instead of a semi-major and a semi-minor axis, or a major and a minor axis, we have a transverse axis between the vertices, and the conjugate axis is between the vertices B and B dashed if the ellipse is on its side, sorry, the hyperbola is on its side, if you like. I'll come back and define that a bit more carefully. And the asymptotes are given by this, and the angle between the asymptotes is given by 2 tan to the minus 1 b over a. Now for the moment, I guess you'll just take my word for that, but where it arises from is the fact that we know that m equals tan theta. So by knowing the equation of the asymptotes, we can get the gradient of each one and tan of the angle that each one makes with the horizontal axis. And then if we use the double angle properties of tan, we can get this relationship. But it's probably something that you would just commit to memory. Now this little point here, notice that if b is greater than a, so the letter under y is bigger than the letter under x, sorry, the number under y, then the hyperbola is compressed horizontally, and vice versa. So if a is greater than b, the hyperbola is compressed vertically. So let's have a look at putting some of this into action. So to sketch the graphs of these hyperbola. So first one, pretty straightforward, just as with the ellipse. We get a, we get b, we use our eccentricity equation to get e, calculate the foci, expecting that they'll be beyond the vertex, which will be at 4, as we can see, what we get when we put y equal to 0. So we get that, the directrices are between the vertices, and the asymptotes plus or minus bx on a have the parabola trapped in there. For our next one, we've got a less than b, so we work out our values of a and b by their position, work out our eccentricity as in exactly the same fashion by that formula. Notice though that the a and the b swap positions, otherwise we've got to learn a new set of equations. And away we go with the foci, the directrices and the asymptotes. So what you can see in this case is that the parabola is compressed horizontally. Now over here, where we've got the same layout but we've just got a sign change, in a sense we've swapped the position of the y's and x's, our our hyperbola is now going to be lying on its side. But we still go through that a is the number under the first thing here, so it's no longer under the x. B is under this, away we go, but when we go to calculate the vertices and the directrices and the foci, then we're going to have to be calculating values on the y-axis. And the equations of the directrices would be y equals something rather than x equals something. Final point, when the transverse and conjugate axes of one hyperbola become the conjugate and transverse axes of a second, the hyperbolas are said to be conjugate pairs. It's a little oddity. I don't think you'll come across it that often. Just store that away in your memory bank. So have a go at 1, 2 and 3 in set 3. Now, in the case when the centre of the hyperbola is not at the origin, not at 0, 0, but at some point hk, our equation takes this form, as you would probably expect. So we could now do number 4 out of set 3 as well.